Good to be back. I want to talk about two things today in today's quantum mechanics lecture. The first is about section 11, this idea of probability current. Loosely, how do you quantify the idea of something flowing, a quantum mechanical wave function flowing through space? Secondly, we've met operators before. We want to look at operators from a more serious mathematical perspective. The role of operators plays a very, very important role in quantum physics, and we want to get more serious, get more precise about the concept of operators and how they're used in quantum mechanics. So let's begin with the first half of the class, which is about probability current. So let's forget about quantum physics for a second and do something slightly mad. Imagine that you fill the whole lecture theatre with boiling water. Okay, so apart from the fact that that would be very bad, you fill the lecture theatre with boiling water, and at each point in space, at each instant of time, you'll have water flowing. So for example, let's consider some point in space, some little volume of space, and the water will be flowing in some direction, shown by this arrow. You go to some different point in space, at the same instant of time, and the water might be flowing in a different direction. We suppose that this is within a little patch of water, and suppose that this is within a little patch of gas, right? And you want to quantify this thing called current for this boiling water filling the room. This idea of current, which is quantifying flow, let's give it a symbol, it's J. That current vector, quantifying the flow, will be a function of both position and time. The faster the little element of water is flowing at that particular point in space, at that particular instant of time, the bigger this current will be. Also, the denser the water, remember this might be within a bubble of gas, of water gas, and this might be within a region of space which is liquid water. The denser the water, the bigger you would expect this to be. So I've just motivated an expression from classical fluid mechanics, which says that the current density, or the current, is the density. This is, in the context of classical fluids, rho would be the kilograms per metre cubed. That will be a function of position and time, times the velocity, and the velocity vector at each point in space, at each instant of time. Now this is an expression from classical fluid mechanics. This is not a course about classical fluid mechanics, but the point is this idea of a current, or more precisely a current density, because this is a current at a point. In classical fluid mechanics, it's proportional to the density of the flowing stuff at each point in space, at each instant of time, and also proportional to the velocity with which it's flowing. Now, we're not going to fill the room with boiling water. We want to fill the room instead with some wave function, some one electron wave function. The question is, this one electron wave function fills the room, it fills the room, and it evolves with time. Question, how do you quantify the idea of flow? If this electron is hooning around the room, it's moving. If it's moving, it's flowing. This is a way of quantifying flow if you're talking about classical liquids, such as boiling water filling the room. Question, how do we quantify this idea of quantum mechanical flow? For a wave function, this will not be the density, this will be the probability density, rho equals mod psi squared. And so we'll have a flow of probability, we'll have a current of probability, and this object, this probability current, is what we want to derive. Now this expression here is classical, it's not going to work for quantum physics. Question, how do we get from the wave function to this idea of a current? Remember, I just want to reiterate that this wave function contains total knowledge of the quantum system, right? So this tells you everything you need to know about the quantum system. If you want to ask the question, what is the current? Properly I'd call this the probability current density, but I could be loose and call it a probability current, or looser still and just call it a current. Yep. So current, probability current, or strictly speaking, probability current density. But to economize words, I'll just call this the current henceforth. Question, if I give you the wave function, what is the formula that would give me this current density? And when I've got the formula, what the hell does it mean, right? That's the question, which we're going to answer now. And as always, one can think mathematically, one can think conceptually, Sometimes we go from concepts to mathematics, sometimes we go from mathematics to... So focusing on the maths, we want to derive an expression for how to obtain the probability current density from the wave function. So let me sketch the maths, and then let me do the maths in more detail. Let this denote the Schrodinger equation. I could take that Schrodinger equation and then multiply on the left-hand side by the complex conjugate of the wave function. I could form a second equation. I write down the Schrodinger equation and I complex conjugate it, and then multiply on the left-hand side by the wave function. If we then subtract, do a little bit of second-year level vector analysis manipulation, then we will end up with an expression for how to derive the current J from the wave function. So that's a sketch of what we're about to do, but let me be a little more precise. I want to write down the Schrodinger equation. So let me write down the Schrodinger equation. M being the mass of the electron. We have the Laplacian, acts on the wave function. We have the potential V. Now V and psi are functions of position and time. To save chalk, I won't write that down. And this equals the energy operator acting on psi. So this is the Schrodinger equation. I now want to multiply on the left. I want to pre-multiply by the wave function psi. So I multiply on the left by the wave function psi, wave function psi, wave function psi. So I've done the first thing. Now I want to form a second equation. I write down the Schrodinger equation once again. And now I want to complex conjugate the equation. You can take the complex conjugate of a number. You can also take the complex conjugate of an equation. Everything here is real, and if you complex conjugate a real quantity, it stays unchanged. Grad squared is not a real number, but it's a real operator. D squared by dx squared is a real operator, and so on. So the complex conjugate of grad squared is grad squared. Psi, being intrinsically complex, becomes psi star. V, the potential, becomes V star, but our potentials V are all real, so I won't complex conjugate the V. I will complex conjugate the psi. I becomes minus I, H bar stays as it is. Psi becomes psi star, and therefore d psi dt becomes d psi star dt. So this is the complex conjugate of the Schrodinger equation, and I now multiply on the left. Sorry, I made one mistake. What mistake have I made? Beautiful. I didn't multiply the first one by the complex conjugate. So I need to pre-multiply, multiply on the left, the first one by the complex conjugate. Thank you. The second one, on the other hand, I pre-multiply just by the wave function, psi. Now this minus sign minus psi. So I have now this pair of equations. What I do next is I subtract them. I won't write that out explicitly, but I will note that these two terms here, being identical, will disappear when you subtract these two equations. What you need to do next is a little bit of second-year level vector analysis, and this is exercise 14. So the next step is to do exercise 14 in the notes. Again, this is nothing more than some second-year vector analysis identities. And what you'll end up with will be equation 52 of the notes. Yep. So d by dt of the magnitude of psi squared, which we know is the probability density, plus the divergence of something. Now, the vector that you're taking the divergence of is something big, so I'm just going to give it a name. In fact, the name I'm going to give this quantity is the current density, but this is something I need to justify. So this is the equation that you get once you take these subtracted pair of equations, do exercise 14, and you'll end up with this, where J, and I've yet to again prove that this is the current density, this object here is some function of the wave function, which is IH cross, twice the mass of the particle, let it be an electron for example, into psi, grad psi star, minus the complex conjugate of this. By the way, since these two terms are complex conjugates of one another, the fact that we have the difference of two terms, each of which are complex conjugates of each other, implies that this is purely imaginary. Multiplied by the I, this thing is manifestly real. In case that didn't make sense, here's a complex number. Here's its complex conjugate. If you subtract the two, the alphas disappear. You'll get twice. You get 2I times beta, which is purely imaginary. Hence, this rounded bracket is purely imaginary. Multiplied by I, this thing becomes real. So two equations here to stare at. I look at this and I see some vector function of position and time equaling this utterly unintuitive mess. Sure, I might think that I'm good because I've got a big equation there, but I don't know what the hell it means, so I'm confused at this point. Then I have this equation here, probability density, and some vector field, which I've yet to do, which is given by this, which I've yet to justify is called the current density J. So I need to do a few justifications here. Before I give you a justification, let me give this a name. It's called the continuity equation. Now, I've already emphasised the idea of quantum mechanics being weird in our first quantum mechanical class. But quantum mechanics is not that weird. And one thing that doesn't happen in quantum mechanics is that things don't just disappear and then reappear out the back of Alpha Centauri. If probability is to flow, from one place to another, it must do so in some continuous manner. This being called the continuity equation is a reflection of that. Let's go back to the analogy of the water. Yep. If this is some volume of space, this is some closed surface in 3D space, and this is a water molecule at point A. So suppose that particular water molecule is at point A at some instant of time. At some later instant of time, suppose that that water molecule is at point B. Then we know that water molecules don't just disappear and teleport and appear somewhere else. That the water molecule, if it gets from A to B, it must do so by flowing through some continuous path from A to B. The fact that water can't just disappear and reappear somewhere else, if I state this more precisely, if the water molecule is inside this closed two-dimensional surface at some point in time, and at some later point in time it's outside, then it must have gotten from the inside to the outside by flowing through the surface. This statement for an arbitrary surface is a statement of continuity. But this was a quantum mechanics equation, and I'm talking about continuity for fluids. This equation is much, much more general. In fact, this is one of the most general equations you'll ever see. This equation is much more general than quantum mechanics. It appears in quantum mechanics, it appears in classical fluid mechanics, it appears in hydrodynamics, it appears in atmospheric physics, it appears in the Einstein field equations of general relativity, it appears in the standard model of high-energy particle physics, it appears in acoustics, it appears in almost every field of physics because, as I'll explain, this thing expresses this general concept, and this general concept is far more general than just the quantum mechanics setting in which we've derived it. In fact, this whole derivation is just forcing the Schrodinger equation to look like this, with a view to identifying this object as the current. But I've yet to justify this. Again, I just want to emphasise the vast generality of this equation. Almost every differential equation of physics and continua in engineering obeys this equation. Even classical particle mechanics obeys this equation, so it's very, very general. So I've talked this equation up enough. I now want to justify it. I want to point out why this is the mathematical expression of continuity in this sense of the term. And the key to seeing Y, this is an expression of continuity. If stuff is to get from inside a volume, closed volume, to outside, it must do so by crossing the surface, hence flowing continuously in space. If it's classical fluid, then the water molecule flows continuously through space. If it's something more abstract, such as a probability density, rho, associated with a wave function, then we're talking about the flow of probability, and this is going to be the embodiment that probability flows quantum mechanically, flows continuously from one point to another. Quantum mechanics may be weird, but it's not that weird for things to just disappear and pop up somewhere else, in the sense of probabilities. All right. So let me just take this continuity equation and write it down again. The rho and j are functions of position and time. I won't write down the r comma t. So I'm writing this thing down again, with a view to understanding what the hell it means. Now, with a view to understanding this, let me consider some volume. And so this is going to be some closed volume, which I'll give a name, and I'll call it omega. I call it omega because when I first started doing research in honours, I worked with a Russian mathematician who gave me lots of Russian mathematics textbooks to read. Apart from the fact they were very hard, they always use the symbol omega for volume, hence I'm passing this on to you. All right, think of it as an upside down V for volume. So this is an arbitrary volume V, arbitrary volume omega, and this is some three-dimensional lump of plasticine in space, but it's a fictitious volume, any volume you want. We can speak of this volume as having a surface, and that surface I'll call del omega. Again, just a piece of notation. So omega is the full set of three-dimensional points inside and on this volume of space with a smooth surface, smooth differentiable surface, and del omega is a set of two-dimensional points which is on this surface. I want it to be differentiable because I need to do some calculus over this surface. All right. I'm just going to take this arbitrary volume of space and integrate the continuity equation over this volume. Now, if I integrate 0 over a volume, I'll get 0. So I've integrated over this volume, and I can have a dx, dy, dz, and I'll just use my abusive notation that I've done before and call that dr. Now, assuming that rho is sufficiently well behaved, in the sense of being single-valued, continuous and twice differentiable, then I can interchange the order of differentiation and integration. For suitably pathological functions, you can't interchange the order of integration and differentiation, but we're talking about a physical field here, a physical wave function psi, which obeys a wave equation, which is the Schrodinger equation. Schrodinger equation has derivatives in it, so it's got to be differentiable. The bottom line is that this thing will be smooth, so it will be twice differentiable. If it wasn't, it couldn't satisfy the Schrodinger equation. This will be twice differentiable, single-valued and continuous. What I call a happy function, what a mathematician would call a suitably well-behaved function. All right. Again, mathematicians will be more precise still. They'd say that this function belongs to a certain set of functions or class of functions which occupies some function space. Beautiful stuff, but I won't go into that now. The point is this is suitably happy, suitably well behaved, that I can interchange the order of differentiation and integration. This thing, remember second year vector analysis. This is a classic case where the Gauss divergence theorem holds. This is the integral over a certain volume of the divergence of some vector field. And you know from second year vector analysis and also from first year electrostatics, that this is equal to the flux of the said vector field through the boundary of the surface. How would I write a flux? Well, it's going to be a surface integral. That integral will be over the surface, over del omega. The flux of the vector field, well, as a piece of notation, let's have some little patch. And this patch will have this little infinitesimal patch on the surface. We'll have an infinitesimal area of d sigma. We can also have an outward pointing unit normal vector, outward pointing normal, which I'll call n hat. And so the flux of the vector field, you take the vector field, you dot it with the outward pointing normal, multiply by the infinitesimal element of surface area, and you've got the flux. Again, this is nothing more than the flux of that vector field, and this all equals naught. All right, so this is the continuity equation, and I just want to take this and put it on the right-hand side. So what this says is the flux of the current density through the surface del omega, is equal to this thing. This is the time rate of change of this 3D integral. Now the claim is that this is a mathematical embodiment of continuity in the sense described by this equation, so this diagram. So this is our link between the concept and the mathematics, So let's have a look at this. We know that this underlined object is the probability that you'll find an electron at a particular position r, at a particular time t, to be within some infinitesimal volume, inside the volume. And the volume of that little cube is dr. Since we're integrating over the whole volume, omega, this bigger underline, this is the probability of finding the electron inside the volume at some instant of time. So it's a probability of finding the electron. If this was a classical fluid, this would be the mass of the fluid inside the volume. This is the time rate of change of the probability of finding an electron within the volume. So suppose that stuff is leaving the volume, probability is flowing out of the volume, then this time derivative will be negative. If stuff is flowing out of the volume, I made one mistake. When I put this d by dt on the right-hand side, I needed to put a negative sign. Yep. If stuff is leaving the volume, then this time derivative will be positive. This quantity on the right-hand side will hence be negative. And that is the flux of J through omega. If probability is leaving the volume, again, this will be negative, this will be positive, and that is the flux, because the flux is nothing more than the rate at which stuff leaves the volume, right? So this is almost a tautology, almost a self-evidently true statement. The rate at which stuff leaves the volume is equal to the rate at which stuff leaves the volume. That's all this is saying. Again, this is a mathematical expression, which I invite you to think about further, of continuity, but not continuity for the flow of a classical fluid, but rather continuity for the flow of probability density. Now, I don't know about you, but I still look at this formula, and while I've justified that this is in fact a current, in the sense of a J that obeys this continuity equation, this incredibly general continuity equation, I'll still stare at this formula and don't get any physical meaning out of it. When I see the formula for probability density, rho, that appears here, this is a sufficiently simple formula for me, the magnitude squared of the wave function, but this thing, I don't like it. It's not sufficiently physically transparent. In an exercise in the tutes, we'll show that this formula can be recast in a form that looks almost identical to the classical result at the top right of the top panel. This can be recast in a form that looks almost identical to this classical result, and we'll look into that into the tutorial, into the next tutorial, which is this afternoon. So let's put this on hold, this complicated formula. I don't understand this right-hand side yet. I do know that it's a current. I do know that it's the promised way of getting from the wave function to the current, but we need to cast this in a more compact and physically intuitive form. That will be done again in the tutorial. In fact, that's exercise 15. I now want to move on to the second half, which is regarding operators. How do we render more precise our knowledge of operators? What's this idea of an expectation value? In quantum mechanics, you have probabilities. So I might say if you measure a certain quantity, you might get this, or you might get this, or you might get this. It's quantum mechanics. But you might say, on average, what will I get? That's called an expectation value. That's something we're going to look at. We also want to look at commutators. This is in essence about the idea that if you apply a certain operator, A, and then a certain operator, B, then the order in which you apply those operators matters. And also complementarity, in the sense of the complementarity principle, in the sense of complementary variables appearing in Heisenberg-type uncertainty principles. I want to emphasise also that all of this is linear algebra. None of this stuff is peculiar to quantum mechanics. So operators can be studied in the context of linear algebra, quite independently of quantum physics. Ditto for expectation values, ditto for commutators, and ditto for the idea of complementary variables. So from one perspective, this stuff can be understood purely from the perspective of linear algebra. But it's also linear algebra applied to quantum physics. Yep. So don't think that commutators or complementarity or expectation values or operators are intrinsically quantum mechanical. They're not. They're far more useful than that. Again, they're used in so many areas of theoretical physics and engineering. Now, you'll remember a very vague statement I made once, which was, here's a wave packet, and this is some, which I call a flying fuzzball, right? This is some volume of space within which the probability density is non-negligible, and outside the probability density is rapidly vanishing to infinity. So this is a flying fuzzball. You could ask the question, what is the centre of mass of that flying fuzzball? What is the expectation value of position? This fuzzball might be evolving through space, but you might ask the question, what trajectory t does the centre of mass, does the expectation value of position follow? If this is a classical billiard ball, then the position r as a function of time is just the trajectory of the billiard ball. If we're doing a quantum mechanical wave packet, hooning through space, evolving through space, spreading, it's going to have its spatio-temporal evolution governed by the Schrodinger equation, as always. Question, how do you calculate that centre of mass? How do you calculate that quantum mechanical equivalent of a trajectory? So let's do that. Now, if it was a classical particle, a point particle, I'd be able to say this is the position as a function of time. Since it's quantum mechanics, there are many positions because this particle is smeared out through space in some probabilistic way. So I'm going to use angular brackets to denote expectation value. So this is to be read the expectation value of position, which is synonymous with centre of mass, the centre of this flying fuzzball. And what is the expectation value of position considered as a function of time? So let's go back to our probabilistic interpretation of quantum mechanics. This is our probability density. This is the probability of finding an electron at point r at some time t. So when we look at this flying fuzzball, right, there's the fuzzball. Here's one particular point in space at position r at time t. This is the probability of finding the electron at that particular point in space. So let's use this probability as a weight, because this is also the probability. I mean, I'm really just saying the same thing twice. This is the probability that the electron is in that little box. This is the probability that this is its position. But there are many such positions. There are many such r vectors. If we were to form a sum of all these r vectors, each of which are weighted by their associated probabilities, then you would have the average r vector, which is the expectation value of position. So we've just learned how to take the expectation value of position, which is good. No duster, that's bad. All right. Let me rewrite this slightly. Instead of rho, I'm going to write psi star psi. And again, let me drop any functional dependence. I mean, the r's integrated out. This is purely a function of time, but let me drop a functional dependence. Rho is psi star psi, and r is in the middle here. So we've just learned that to calculate the expectation value of a given operator, in this case r, what you do is you take psi star and psi. You put the object that you want to take the expectation value of Okay, this is the position vector r, but it's also an example of an operator. And we calculate the expectation value this way. And this is generalized. If I now have any operator, I could call it A, I could call it A hat. This is any operator. This might be the energy operator. This might be the momentum operator. This might be the position operator. This might be the number 2, any operator. And I want to calculate its expectation value. Then I just do exactly the same thing. Take psi star. I put the operator in the middle, A or A hat, whatever I want to call it, and the wave function. Now you might say, why did I put A star, why did I put psi star psi and stick A in the middle? Here it doesn't matter because psi star and psi and r are just numbers or bunches of numbers, and order doesn't matter. With operators, order does matter. So this actually corresponds to a particular choice. There is a degree of arbitrariness here, but this is, again, a choice that works. It's consistent with the experiment. Other choices are also consistent with the experiment, a point that I won't go into. Remember before, we had this idea of the wave function as sort of sitting on some cloud in the sense of describing total knowledge of the system, and that you can have an operator A, and that operator A allows you to extract some physical quantity from the system. Now earlier I told you a lie, and I'm sorry about that if the operator acts on the wave function, you get the eigenvalue A times the wave function, and this was a way to calculate the expectation value of that operator, which might be some physical quantity. Energy operator, energy. Momentum operator, momentum. Position operator, expectation value of position, namely centre of mass. This wasn't a lie, but it was a restricted statement, because this is an eigenvalue equation. Operator acts on eigenfunction to give eigenvalue times eigenfunction. And you might ask the question, well, what if psi, the wave function, is not an eigenfunction of the operator? Then this will not be a way of extracting A. You know, when you take the measurement of this of the associated quantity, you may get any one of a number of quantities. What I've just taught you is something more general. If you have an arbitrary wave function, which is not necessarily going to be an eigenfunction of the operator, then we want to ask the question, what is the expectation value? What, on average, will we measure when we measure the physical quantity associated with A? And this, the answer is the expectation value calculated as follows. So I could write down examples of the expectation value of momentum, the expectation value of energy. We've already done the expectation value of position. So just as one example, suppose that we had the momentum operator P. Sometimes I write that as P, sometimes I put a hat on it. That hat is not a unit vector. This is denoting an operator. Context will tell you whether a hat denotes a unit vector or an operator. Expectation value of momentum, we just follow this through. Integral of psi star, momentum operator, which is minus I h cross grad, minus I h cross grad times psi, and then dx dy dz, which I write as dr. This is not one equation, this is 3 scalar equations. Its x component will be the expectation value of the x component of momentum, psi star. X component of grad is d by dx, psi dx dy dz, and similarly for y and z. Again, I emphasise that all of this, exactly the same expressions would appear if I was giving a linear algebra lecture, but I'm not. So the point is that this is not explicit, this is not intrinsically quantum mechanical. These are tools of linear algebra used to help with quantum mechanics. Let's go back to this general expression. I want, this is fairly abstract. We're using expectation values of a given operator. This is representing some physical quantity to extract a meaningful quantity, the expectation value of a measurement. But I know that when I take any measurement on a voltmeter, an ammeter, a crow with a ruler, any physical measurement must be real. So the numbers that you measure when you do physical experiments must be real. So we're going to demand that this operator have a real expectation value. And as we're about to show, the demand that the operator have a real expectation value implies that this operator A can't be any old operator. It has to satisfy a certain condition. It has to be Hermitian. Now, you've met the concept of a Hermitian matrix in linear algebra. That idea of a Hermitian matrix is ultimately equivalent to the idea of a Hermitian operator, and we'll see that equivalence later. But again, a piece of language from linear algebra appearing. By the way, sometimes this is an I, sometimes this is an E. It's named after the French mathematician Hermite, and there's two different spellings. I don't care which spelling you use, but I'll consistently use this one. So from a purely mathematical perspective, we want this to be real. That means that that's going to place a certain condition on this operator here, and operators that obey that condition will be spoken of as Hermitian. Now this is physics. These are not arbitrary functions. These are functions of physics. These are wave functions that obey the Schrodinger equation. These are not any operators. These are not any linear operators. These are operators that give real expectation values because these are going to be the results of measurements. So we're going to give these operators a name. Since they're corresponding to physically observable quantities, we're going to call these observables. Strictly speaking, the concept of an observable, in order for an operator to be a linear operator to be an observable, it needs to satisfy two things. First of all, its expectation value must be real. Second, its set of all eigenfunctions must be a complete set. So in order for A to be an observable, it must satisfy two conditions. Number one, its expectation values must be real. And the second is that its set of eigenfunctions must be complete in the sense of a mathematically complete set, which we described in an earlier class. I won't dwell on that latter point because it's fiendishly difficult to prove. It's way beyond the scope of this course. In fact, it's way beyond my limited intelligence. I don't know how to prove it myself, except in certain limited circumstances, and neither do most physicists. Sorry about that. All right. We want to focus on the idea that these wave functions, that these operators have real expectation values. What restrictions does that place on those operators? Well, the reality of this expectation value can be expressed in a succinct mathematical way by saying that the expectation value of A and its complex conjugate must be the same. What is the expectation value of A? I'm on equation 68 here. It's the integral of psi star A psi dr. Let me just drop the dr. So let me put it in. And this equals its complex conjugate. The same thing with a complex conjugate. Now, on the right-hand side of this expression, what I want to do is to bring this complex conjugation inside the round brackets. And so when I do so, we need to be a bit careful here. This is an integral. This is a sum of objects. Yep. And you know that if you sum two objects and complex conjugate them, then that'll be the sum of the complex conjugates. The fact that this is a continuous sum doesn't change that fact if, and I stress this, if psi is suitably well behaved, which it is. I'm going to interchange the order of complex conjugation and summation. So I'm going to bring the complex conjugation inside the sum, inside the triple integral. So I've got the function psi star, which is complex conjugated, again, to give me psi. I need to be a bit careful. A is an operator. Operators act on functions to give new functions, right? So this thing that I've circled is a function. It's a result of applying the operator A to the function psi to give some new function called A psi. So let's complex conjugate that whole thing because we brought in the complex conjugate. It's hopped in like a frog. And by the way, frogs will appear many times. Frogs, as in the things that hop around, will appear many times in quantum mechanics for reasons that you will see soon. Not today's class, but soon. because I set myself the challenge of introducing a frog analogy for every lecture from today henceforth. So if I don't introduce a frog analogy, then throw a frog at me. All right, bring the star inside. Yep. A psi star, dr being intrinsically real is still dr. So that's it. The reality of the expectation value of A implies that this left-hand side, and I could put a bracket here if I wanted to, makes no difference. This is equal to the right-hand side. So if you just pick up any operator, any linear operator A, then in general it will not obey this condition, right? In order for the expectation values to be real, again, this is nothing more than, this is purely linear algebra, not intrinsically quantum mechanical. In order for the operator A, I could call it A, I could call it A hat, to be a necessary condition for it to be an observable is that its expectation value be real. It must satisfy this condition for any wave function psi. So I give you a particular operator A, then it must satisfy this condition for any well-behaved wave function psi. If it does, then we would speak of A as being Hermitian. And that's a necessary condition for it to be an observable in the physics sense of the term. Proving the Hermitian nature, or to introduce a related word, proving the hermeticity of a differential operator, of a linear operator, is something we need to show in the context of quantum mechanics. Is the energy operator Hermitian? Is the momentum operator Hermitian? Is the position operator Hermitian? These things need to be proved and will be proved in exercises, some of which will be covered in tutorials. I just had a mental blank. I'm trying to think of what to say next. Yes. You've met the idea of Hermitian operator, of hermeticity before. I've just given you the idea of a Hermitian operator. But you've also met the idea of something being Hermitian in the context of matrices. You've heard about a Hermitian matrix. A Hermitian matrix, again, above quantum mechanics, in the theory of matrices, a Hermitian matrix is if you take that matrix and you complex conjugate each element and then transpose that matrix, you get the same matrix. Yep. Just to repeat, a Hermitian matrix is a matrix which, if you take complex conjugate each element and take its transpose, you get the same matrix. Hermitian matrix, Hermitian operator. How do these two things mix? They mix as follows. So far we've been doing wave mechanics. We've been treating physical systems with a wave function, which is governed by a wave equation, or more precisely governed by the Schrodinger equation. There are infinitely many ways to do quantum mechanics. Electrons don't know about the Schrodinger equation, and you can describe the physical system in an infinity of equivalent ways. By the end of this course, you'll be able to do quantum mechanics infinitely many different ways, with infinitely many representations. When Schrodinger was developing the Schrodinger equation and wave mechanics, which needed this idea of Hermitian operators, his arch-enemy Heisenberg developed a different system of quantum mechanics called matrix mechanics. Instead of describing physical quantities by linear differential operators or linear operators, he used matrices instead. Instead of describing physical systems with wave functions, as you do in wave mechanics, psi, he instead used column vectors. And the theory of matrix mechanics developed contemporaneously with and independently of wave mechanics. I mean, these guys hated each other and didn't want to talk to each other except when they were arguing. You can develop quantum mechanics from a matrix perspective. We'll actually learn how to take Schrodinger's wave mechanics and recast it in terms of matrix mechanics. These two theories are equal, and we'll prove later that Hermitian operators, when you go over to the new way of doing quantum mechanics, matrix mechanics, Hermitian operators are represented by Hermitian matrices, and so these two usages of the term Hermitian are equivalent. It's also setting up a beautiful and profound connection. I mean, here the language is one of linear operators linear differential equations. With matrix mechanics, you're talking about linear algebra, linear equations. Is there some connection between linear differential equations and linear algebra? Is there some connection between linear operators such as d by dx, energy and momentum, and associated matrices? Is there some link between functions and column vectors? The answer is yes, absolutely. And there's a beautiful subject called functional analysis, which sets up an equivalence between the theory of linear differential equations and the theory of linear systems, Hermitian operators, Hermitian matrices, functions, column vectors, linear operators, matrices, differential equations, systems of linear equations. And this connection is very much at the heart of quantum mechanics, as is this translatability from wave mechanics to matrix mechanics. Again, that's going to be a topic of future classes. I now want to talk about commutators and complementarity. So this is section 12.2. Commutators and complementarity. So we have operators A and B, let's say. The order in which you apply those operators matters in general. If A and B were matrices, the order in which you multiply two matrices, A times B or B times A, matters. If A was the operator put on your shoes and B was the operator put on your socks, then the order would matter, right? Mathematics is no different. The order in which you apply two operators, let's say A and B, matters. In general, AB will not equal BA. How do we reflect this mathematically? The fact that AB minus BA will not necessarily equal naught if A and B are linear operators. We introduce this idea of a commutator. So this is a definition, A comma B in round brackets. By definition, triple equal sign is AB minus BA. If two linear operators A and B commute, then this commutator will vanish, it'll be 0. If two linear operators don't commute, then this commutator will be non-zero. This idea of non-zero commutators can be encapsulated, for example, if you take the x position and the x component of momentum, this is exercise 20, those operators will not commute. In fact, they equal IH cross. Similarly for y and the y component of momentum, similarly for z and the z component of momentum. Similarly for the energy operator, which is IH cross d by dt in time, none of these pairs of operators commute. This fact that pairs of operators don't commute is intrinsically linked to an uncertainty principle, and I'll begin the very next class with that idea. So let's look at one of these things. You know that position and momentum don't commute in the sense that their commutators don't vanish, but you also know that there's a position momentum uncertainty principle. Yep. You also know that there's a position momentum uncertainty principle, and this is an uncertainty in the measurement of x. X might have a particular expectation value, but it can also have an uncertainty, which we'll make precise at the beginning of the next class. Similarly with momentum. This is an uncertainty principle. Is this linked explicitly to the non-commutativity, the fact that, of two operators, the fact that x and px do not commute? The answer is yes. Exercise 21, which is really hard. I can't do it without looking at the solutions, and I've done it 20 times before. Exercise 21 is hard and therefore optional, not examinable. Gives you a link between non-commuting operators and an associated uncertainty principle. The uncertainty in some operator A times the uncertainty in the operator B. If that equaled naught, then you could measure both with arbitrary precision, but you can't if that right-hand side is not naught. This is a generalised uncertainty principle. Here's the commutator. If that vanishes, the right-hand side is naught, and this product of uncertainties, which I would call an uncertainty product, is bounded by 0. In other words, there's no condition. But if this commutator is not naught, evaluate its expectation value, take its magnitude, and that will be the right-hand side of your uncertainty principle. The non-commutativity of linear operators associated with observables implies an uncertainty principle, and the position momentum uncertainty principle, the energy time uncertainty principle are all special cases of this formula. I'll begin the next class by going through equation 72, rendering precise the idea of uncertainties, and then we'll talk about how to get from quantum to classical. That's it. Thank you. As always,